Semantic annotation is the process of transforming a non-semantic data format such as JSON into the semantic data format, RDF. Semantic translation is the process of transforming RDF data into different RDF data. In this video, I will show you how to do both of those using our Semantic Annotator and Semantic Translator, both products of the ASSIST-IoT project. The software that I will present, that we call Enablers, is designed to be primarily used with data streaming over Apache Kafka, MQTT, or both at the same time. I will go over the basics, and if you need to learn about specific configuration options, use cases, limitations, advanced use examples, you can read all about it in the technical documentation. All links are in the description below. There are a number of options that you can use to install our software, including Helm charts, Docker files, Docker Compose files, or you can compile everything from code yourself. The code is licensed under Apache 2.0, so you can freely download it and play around with it as you see fit. I will demonstrate the quickest way to set everything up with the Docker Compose file included in the code. Other possibilities are described in the documentation. To install the software using Docker Compose, all you need to do is download the code. The links are in the description. Navigate to the directory where the code is downloaded and run the command docker compose up. The first time you run docker compose up, it might take some time as the images need to be downloaded and the software needs to be compiled, but eventually you should see that all the containers are up. To verify that everything works correctly, you can go to your web browser and call up the REST API exposed by our software. For Docker Compose installation, the port number that you need is read from the .env file. If we see what's inside this file, we see that the REST port is number 8888. So now if we go to localhost on port 8888, this will give you the REST API for our software. The first endpoint that you can visit to see if everything works could be, for example, /version. And if you want to see something better, go to /swagger, and this will give you the full documentation for the API. What I've shown you was the Docker Compose deployment for the Semantic Annotator. The deployment for Semantic Translator is equivalent, only the number of exposed if it's on the same machine should be different. In my case, it's exposed on localhost port 8889. And to go to the Swagger documentation, you actually have to call up a different port, which is v1 for version 1, API export /docs. And there we go. So now we have our software deployed and access to the REST API with Swagger documentation. So before diving deep into the software, let's spend some time trying to understand what it is that it actually does. Let's take a look at the semantic annotation first. The process of semantic annotation, or semantic lifting, is the process of annotating data using an ontology, thus making the data semantic. So, for example, if we had as input the JSON on the left, very simple JSON, and wanted to make it semantic, to turn it into RDF, we could end up with something like presented on the right, which is RDF in the turtle serialization format. This mapping seems very simple, but still we need a way to define it. And for that we turn to the technology called RML, which is RDF mapping language. Now, RML can be a very expressive language, but it can also get a little bit complicated. And there are many tutorials online that will do a much better job explaining the full extent of what it can do than I can in this video. That being said, there is an easier alternative to RML that is actually compiled to RML, which is called YARML. And we can use the online tool Matey to offer our YAML files that we will then turn into RML and eventually load into our semantic annotator. The link to the Mate editor is in the description below, and the first time you open it, you will be greeted with the A-person example, which is a different example than what we want to map. So the first thing I will do is to put in our data and then go on to edit the YAML file. Since we're mapping a JSON file, the language that we will use to select data from this file is called JSON path. It's a very intuitive language, so the first thing we define is the baseline selector. For the example, that was the array of persons. In our example, we only have one top-level object, which is what we will select with the $sign JSON path selector. Now remember that this is what we want our RDF code to look like, so what we need to do is change the subject of this base triple that we have and attach the properties of RDF type and name and last name to it. To do it, we will use the YAML structure of defining a subject and an array of property object pairs. So here S stands for subject and PO stands for property and object pair. So what we want to have is a different IRI. We want to have example.com/person. Then we will select a different property, which is ID. And I will copy that to put the last name here. And select the last name from my JSON. With that done, I can click on Generate RML, which will generate the actual code being used to define the mapping, and generate the link data to see if the output is as I expected. And I think everything looks fine. So this is how we can quickly iterate and test if your YAML files, or in our case RML files, are correct. Now, before loading this RML code into Semantic Annotator, we need to turn it into Carmel code. Now, Carmel is a dialect of RML. It's not exactly the same, but luckily the changes that you need to make to an RML file to turn it into Carmel are quite small. And I will show you exactly how to do it. To turn RML into Carmel, copy the RML code, go to your favorite editor, paste it in, you can add the Carmel URL prefix for convenience. Now, I admit that I don't know this prefix by heart, so I will just copy and paste it. Next, find the RML source and change it from the string data JSON to an anonymous entity of type Carmel stream. Save the file, and this is what you need. This is how you change RML into Carmel that we can use in our semantic annotator. To apply annotation or translation in a streaming fashion, we use the abstraction of a so-called channel, an annotation channel or a translation channel. Now, a channel is something deployed on top of a streaming broker that uses topics from a streaming broker as input and output. So it reads input from the input topic, processes, so annotates or translates data, and outputs the result on the output topic. A simple annotation channel definition looks like this. We have some metadata with name, description, and so on, and the most important field, the mapping, which contains the RML field with JSON encoded Carmel code that we just prepared. The input and output format also very important. They define how the input will be read. So here we have the option of JSON, XML, or CSV, and the output, which defines the serialization of RML that will be written to the output topic. Settings for the broker are as following. We have the input topic settings and the output topic settings. And here I decided to mix it up a little to read the input from an MQTT topic on my local broker and write it to a Kafka broker, also deployed on my local machine. It's important to mention that because our software works on streaming brokers, you have to deploy the streaming brokers themselves. They do not need to be deployed locally, they do not need to be on the same machine, but they need to be accessible through the network. So I have my two local deployments of a Vern MQTT broker and a Kafka broker. You can quickly set both of those up using Docker. I will leave some useful links in the description for that. So for both input and output topics, we need to define the topic names. So here we have demo/input, and the output topic would be demo_output_TTL on the Kafka broker. Unfortunately, the Kafka broker does not support slashes in topic names, so we cannot be consistent here. Let's use this channel definition to define an annotation channel using our REST API. And for that, I will turn once again to the Swagger documentation. So let's copy this code, go to our browser, to the Streamer API, and here we have the API group for defining the channels. So posting the channels will add a definition of a channel. Let's execute and see what the response is. Here we have the response body. The server responds with the ID assigned to our new channel. Now, to see if it actually works, we have to test it with the brokers. And for that, I will use the MQTT Explorer to send the input data. And I have an instance of a Kafka UI to see if the message was received. The topic name for our input on the MQTT broker was demo/input. So let's go to MQTT Explorer and try to send a message to that topic. I will paste the JSON that we prepared and publish it on the broker. So here we have the input message. It was correctly received by the broker. And let's go to Kafka UI to see if it was also annotated and received by the Kafka brokers. So going to topics, we see the demo/output/TTL. Checking the messages, we see that here there is an annotated message exactly as we expected. We can also change some data. Send it again. And we have another message annotated just like we expected. Now that we know that our basic annotation channel works, I have to admit something. I lied to you. You see, the input and output topics are not the only topics for an annotation channel. The message goes through a number of stages, and at each stage, auxiliary message may be output from the whole process. So other than the input and output topics, we also have the input and output monitoring topics, which output a simple message, a confirmation that something went through that stage, but also the error stage, which will output any errors that may occur while annotating. So let's define a bit more advanced channel to make use of those additional topics. This is the definition for our more advanced annotation channel. The kernel code is the same, so the transformation done will be the same. Only this time I decided to use JSON-LD as the output format because I like JSON. For the input and output topic settings, we will this time use the same broker, so MQTT. As you can see, this time I didn't define any connection data, any passwords or even IPs, which means that the default data configured on startup will be used. This is just a shorthand to avoid putting the same configuration every time you need to define a channel. So we will be using the same input. So we will have two channels with the same input, but different outputs, just to distinguish the output format that we are using. And we will also define the input and output monitoring topics, as well as the error topic. The additional topics, meaning the error and input and output monitoring topics, may be switched on and off as the channel is running. So if you decide after the channel is created that you actually don't need that extra information, you can switch them off and turn them on back again once you change your mind. So let's load this definition into our REST API. Let's create a new channel. And it seems that the channel was created. So let's test if it actually works. I will send the same message as before, maybe change the ID just to see that the transformations are still applied correctly. Publish it. And now, on top of the output on the Kafka broker, you can see we have the third message annotated here. We also have an output from the channel that we just defined on the MQTT broker. So we have the output in JSON LD, which is equivalent to the turtle output because the transformation is the same. We just defined a different output format. On top of that, we have the input and output monitoring topics that tell us what the timestamp of the received message was at the input and output stages of the annotation channel. You may notice that we don't have yet output from the error topic because there was no transformation error. But if I mess something up, let's say I send a misformatted JSON file. Here we have an error. There was an exception parsing the error, unexpected end of line input. And once I fix it, the message should go through just fine and once again appear on the output. So this is how an advanced annotation channel works. If you're curious about what options exactly are available for definition of channels, transformations, and so on, we have written documentation available online. You can also see all the data schema here in the Swagger documentation, both for the annotator and the translator. Speaking about the translator, let's move on to semantic translation. The semantic translator is an independent piece of software, so we can use either annotator or translator independently, or you can actually connect those two because the output from the annotator is always RDF and input to the translator is also always RDF. What the translator does is it changes the ontology with which the RDF data is described. For example, if I take the output of the semantic annotator that was data described in RDF with the example.com pseudo ontology, let's call it that, and wanted to change my data so that it is expressed with schema.org to end up with something that we have on the right side of the screen. For that task, I would use the semantic translator, and the definitions of how the transformations are done are described in a format called IPSM AF. AF stands for alignment file because the transformations are called alignments. IPSM AF alignments are expressed in an RDF format. We have here a lot of metadata and a lot of prefixes. But what is most important in every alignment are the so-called alignment cells. An alignment file can have any number of cells. Here, because the transformation is so simple, we only have one. Every alignment cell contains two entities and some optional transformations. The first entity, called entity 1, defines the pattern that the translator will look for in our RDF data. whereas the entity2 defines the pattern to which this data, if found, will be rewritten. Both are expressed in the format that is very similar to SparkQL queries. It is actually just the simple SparkQL queries which are equivalent to the Turtle format, with one exception where any variable or any IRI with the var prefix, which stands for variable, will be treated as a Sparkle variable. So if you are familiar with Sparkle, you will feel right at home using those patterns. So here, what we want to select from our input data is anything that is of type FOAF person, has a name and last name from the example ontology. And the way we want to rewrite that is to put the name under schema.org given name property, the last name under schema.org family name, and additionally we want to have the concatenated name under the schema.org name property. The concatenated name is output from a SparkQL function concat, and we define this transformation in the transformation tag. We may have more alignment cells, and for each cell we may have more transformations. This is just a simple example to show you how it works. The return value of this function will be put under the schema.org name property. So let's see how to define a translation channel using this alignment. I will copy this code. The difference between how the semantic annotator and translator work is that because the alignment files tend to be much bigger than the annotation files, you need to upload them first to the semantic translator before you can use them. The semantic annotator also has an option to upload the annotation files beforehand, but you don't need to use it. You can define the transformation directly in the channel definition. So, to upload an alignment into the semantic translator database, I will once again use the Swagger API because I'm lazy like that. Let's paste in the code, execute, and the alignment was uploaded successfully. Next, we will need to define a channel that uses this alignment. A channel definition for the semantic translator looks much simpler than the one for the semantic annotator, mostly because we will refer to the alignment that we previously uploaded to the internal database as opposed to putting the transformation data inside of the channel definition. So what we have here is we need to define whether it's a channel that goes from MQTT to MQTT, from Kafka to MQTT, from Kafka to Kafka, and so on. So the channel type, the shorthand for MQTT to MQTT is MM. Once again, we will use the default connection data that you define before starting the software. The input and output topics for the semantic translator are called source and sync for compatibility reasons with the legacy versions of this software. So here we will read the input from the demo/output/JSON-LD topic, and you may remember that this is exactly the topic that we defined as output from one of the channels of our semantic annotator. And in this way, we will connect the semantic annotation with semantic translation. Here we define the so-called input alignment name and version. We also have an option to chain two alignments. One is called input alignment, another one is called output alignment, but this is just optional. If you want to know the reasons why we decided to design the software this way to allow chaining of two alignments within one channel, please read all about it in the documentation. The sync, which is the output topic, will be called demo/translation/output. So I will copy this channel definition and again put it into the Swagger API. And the channel was created successfully. Now, going to my MQTT Explorer, let's once again send another message and see what happens. So the previous channels from the annotator are still active, so we still have the output for the JSON LD and the output on the Kafka broker. But this time the output, the JSON LD output to be specific, is read by the semantic translator and output on the appropriate topic. So here we have the JSON LD that was produced by the translator based on the JSON LD produced by the annotator, which was in turn produced from the input data, the original JSON. Here is the simplified diagram of the annotation and translation channels that I presented in this short demo. If you have any questions, if you need some support deploying or using our software, feel free to reach out and read the online documentation. We have much more complicated example and use cases described there. Have a nice day and goodbye.